Hello everyone, my name is Alex Lemmy, and today I want to present the paper we submitted to a poster for the paper we submitted to the AABI 2021 Symposium. VIB is half Bayes. Paper is on the archive. Please check that out for more information. This is going to be brief. I want to highlight my colleagues, Warren Morningstar, Ben Poole, Ian Fisher, and Josh Dillon. All right. Really, the point of our paper is to try to explore a middle path, a middle way, a Goldilocks type scenario that is somewhere sort of halfway between a fully Bayesian approach and empirical or maximum likelihood style approaches. I want to motivate that with a simple sort of toy example. Imagine I have some regression task. I've got true data, a true data distribution that is some uniform on some interval, and it has a Gaussian at each position. Now, from this true distribution, I could draw data, and I want to fit a model to it. What if I try and build like a neural network? But importantly, that neural network can express, not only a prediction to each location, but some uncertainty, right? Like it itself is a predictive model that has some measure of uncertainty. So here's a randomly initialized neural network. Doesn't do a particularly good job, but it shows you the kind of things they can express. Traditionally, what would we do? Traditionally, we would, given finite samples, we would do maximum likelihood. We would try to just adjust all the parameters of our model until they do the best job of explaining the observed data that we have if we only had 10 data points. But of course, there's a problem, right? Our model overfits. In this case, the model will perfectly go through each of the 10 data points, but because it can express its own uncertainty, it decides to be as uncertain as it possibly can on those 10 data points. And so it becomes very tight, squeezes down, and goes exactly through those 10 data points. And as such, it does a terrible job of actually predicting the true distribution that we're interested in, right? The orange thing. The blue curve looks nothing like the orange curve. The traditional way to deal with this, right, in the world of big data is you could, instead of having only 10 points, we could do 100 points, and it looks better. Or we could do 1,000 points. If we kind of have enough data, then the model sort of starts behaving. It can't hit all the data exactly. It's sort of regularized, and it does a great job of kind of matching things. If we could have an infinite amount of data, if we could sort of never stop, if every mini batch in our training had a new and unique data point, then we would do a fantastic job. But of course, we don't always have an infinite amount of data. Oftentimes we have embarrassingly little data. And broadly speaking, Bayesian inference is one of a set of techniques for dealing with that. Bayesian inference, you do some math, but what it allows you to do is it allows you to kind of prove or offer certain guarantees that if you train using only a finite number of data points, you are still optimizing a thing which is a bound on the thing you actually care about. You can, on finite data, optimize a thing which is guaranteed to always be above what would happen if you had infinite data. And Bayesian neural networks, they can do a great job. On tasks like this, the simple regression task, they can do a good job of not overfitting and kind of matching the true distribution. But they're expensive. We all know this. They're hard to sample. It's hard. Variational Bayes is hard. They're expensive. We have this whole workshop. It's difficult. So what if there was something in between? And that's sort of what we wanted to explore in this work. What if, for something like a discriminative task where there's actually two variables, there are x's and y's, what if, instead of trying to be fully Bayesian and protect ourselves and offer guarantees about what would happen with infinite numbers of x and y points, what if instead we were okay with the fact that we only could evaluate our function at a fixed number of points, like let's say 10 positions here? But what if we had access to an infinite number of targets? What if we could, have an infinite number of y values at those 10 locations? In that case, if you fit like the neural network regression, it can actually do a really good job. It can match the model very well at those 10 points, and it does a reasonable job of interpolating between those 10 points. Once you start extrapolating, the model kind of goes a little haywire, but this is a pretty decent model and actually kind of quantitatively does nearly as well as the fully Bayesian approach. And then really the rest of our paper is you can do the math. The same mathematical guarantees that a Bayesian can use to try to protect against finite number of joint samples, you can try to protect yourself against a finite number of target samples, and then try to just be empirical about the finite number of X samples. Turns out that this is a previously named approach called the Variational Information Bottleneck. The objective becomes equivalent to that, but it's a middle ground. It's a way of trying to protect yourself against a finite number of targets, samples, while just being brazen and foolhardy about the fact that you only observed a finite number of X positions. And that's really the kind of the whole story. This is very much an elevator pitch, but maximum likelihood overfits. Bayesian approaches do well, but are expensive. For certain kinds of problems, if you could only have multiple target samples, but a finite number of input samples, you can still do reasonably well. And it turns out you can turn the same mathematical crank that got you from here to here, but you can turn it only on the Y targets, and you end up, with an objective that people have studied, but one that I think this community would be interested in. The end. Thank you very much.